Hi guys, in this video, let's recap the method of sections to solve the bending and the shear at a given point along the beam. Particularly when you have a simply supported beam with multiple loading conditions, and it's difficult to solve at the bending and the shear at a given point. So in this case, we can use the method of sections. For example, in this case here, we've got UDL and a point load along the beam, and by using equilibrium equations, we can quickly solve the reactions for A and B. But the question is, when we start drawing the shear force diagrams, we know from the equilibrium equations, we know the reaction at the point A is 5.13 kilonewtons. And we can draw a straight line to point C because nothing in here. And from C to D, and we know it's going to be a sloped line because it's UDL. So the matter is, what is the shear force at the point D? In this case, we're going to use the method of sections to solve it. So we can separate the A and D, the segment out, coming back to here. So we draw a straight line, putting A and D, and we mark on the section, on the reaction A is going to be 5.13 kilonewtons. And then we draw UDL on top of it between C and D. And we also have got, and if you cut, because you cut, we wouldn't know what shear force is at D, so we cut at the D. Therefore, we've got a shear force VD coming down. In this case, because remember, when you cut at any point, at this point, the action and reactions must be equal. That means you've got reaction A 5.13, it has to be equals to whatever the loads coming from up. That is 2 kilonewtons meters times your distance is 3 meters plus your VD. So these forces has to be equal to your reactions, 5.13. Therefore, you can calculate your shear force at D as negative 8.7 kilonewtons. So in this case, now it's getting it's simpler. Now we can use this shear force diagram to connecting C and D, because D is negative 0.87. And coming to D, that is a straight line because nothing in here. But at the point E, we've got a 4 kilonewtons concentrated load that's come down to 4. That gives the 4.8 kilonewtons. And between E and B, there's nothing in here, a straight line. And we have to, and it must come back to 0. That is a 4.87. This total area, this length in here is a 4.87, which is exactly what we calculated. RB is a 4.87. Okay? So in this case, let's summarize. When you do a section cut, just make sure whatever comes down must be equal to whatever comes up. So that's the trick. Don't get that wrong. Okay, if you have any questions, or make a comment below, and we'll see you on the next video. Thanks.